This video is a continuation of the previous paper where I looked at the first 10 questions in paper 1 of the May-June session of 2020, and in today's video I want to look at the next 10 questions, that is question 11 up to question 20, and let's go straight to question 11. Now in question 11 we are told that a wooden block rests on the rough surface of a board. Notice that the surface is rough. One end of the board is then raised until the block slides down the board at constant velocity v, and you're given that diagram over there. Then you're asked, what describes the forces acting on the block when it is sliding with a constant velocity? This question requires us to look at the choices given because there are so many things we can say about an object which is sliding down an inclined plane which is rough and it has constant velocity. First of all, we can be able to consider the forces acting on that block. So one of the forces which is acting on this block is its own weight, and we represent that with an arrow which is drawn vertically downwards, and we call it mg. How do we tell that it is vertically downwards? This arrow that you draw should always make 90 degrees with any horizontal line, and this is such a line. So that is how you make sure that that is the case. The board is usually inclined at some angle theta. So we are able to resolve this force perpendicular to the incline this way, which will be mg cos theta, and then parallel to the incline like this down the incline, which will be mg sin theta. And because we are told that this board is rough, there will be frictional force acting on this block, and this force acts along the contact surface like that, and it will act in the opposite direction, and we call it frictional force. And this is mg sin theta. Don't forget that. It is the component of the weight down the incline. There will be this force where the board exerts a force on the block perpendicular to the incline. It is actually opposite this one, and we call it the normal component of the contact force. This, we have just said that it is mg cos theta, like that. Those are the forces which are acting. Now, given that this speed is uniform, it's constant, it means that the acceleration is zero, which further means that the resultant force on this block is zero. And if the resultant force is zero, it means that mg sin theta is equals to the frictional force. Or you can say mg sin theta minus friction force is equals to 0. You know, when we resolve vertically downwards, we can use the equation force is equals to ma. Down the incline, we can resolve those forces down the incline and say mg sin theta minus frictional force will be equal to mass times 0, because the acceleration is 0. In which case now, if you bring this one to this other side, you are going to say friction force on this side is equals to mg sin theta, and that is what I've already stated here. Now, that is the information that is required when you are looking at an object moving down an inclined plane which is rough. Now, let's look at the choices given here. Frictional force acting on the block. They're saying it is down the board, it is down the board, up the board, up the board. So we know that friction force is up the board. So it is either C or D. Let's look at the resultant force on the block. It is 0. You can see by knowing exactly what happens to an object which is on an inclined plane, you're able to answer any question given over there. So it does not matter what the examiner might bring. Arm yourself with the necessary knowledge as far as an object sliding down an inclined plane is concerned. And I've dealt with this concept extensively in one of my online courses, which is Mechanics 1. Just to check on the video up there, and if you're interested, you can have a look at the free lectures that I offer there, and they can be of much assistance to you. So let's go to question 12 and see what we have. Okay, in question 12, we are asked, which statement best describes a couple or moment of a couple? We know that a couple is simply a pair of forces. Like, for instance, when you look at the steering wheel of a car, there's the steering wheel. Let me just draw a realistic diagram of how maybe the steering wheel of the car would look like. You know, something like that. The driver holds the steering wheel with both hands. So when you turn the steering wheel, one of the hands will pull this side this way with a certain amount of force. The other hand pushes the steering wheel that way at that point with the same amount of force. These two forces are usually of equal magnitude. Equal magnitude. F, for example, of 20 newtons, F 20 newtons. The magnitude is the same, but the direction is opposite each other. The two forces are parallel with each other, and they tend to turn this system about some point here at the center. So moment of a couple is given as just one of the forces, just get one of the forces, times the perpendicular distance between them. This will give me the moment of the couple. But a couple itself consists of two forces which are of equal magnitude, parallel to each other, and they act in opposite direction. And then they don't share the same line of action. Those factors are very important. Equal in magnitude, they act in opposite direction, they are parallel, they are of equal magnitude, and they don't share the same line of action. The line of action of this force on the right is this one, while the line of action of this force is this one. That is how a couple looks like. Now, armed with that, and I always insist that when you are answering such questions, you must arm yourself with the necessary knowledge. So armed with that, let's look at the first choice. In the first choice, they are telling us which statement best describes a couple. A pair of forces of equal magnitude, that is correct, acting in opposite directions, which produce rotational motion but not translational motion. This is true. It produces rotational motion. It makes the object to rotate about a given point. Like, for example, this steering wheel rotates about this particular point here. So that is true. Let's look at the next one. A pair of forces of equal magnitude acting in opposite directions, which produce translational motion but not rotational motion. This is what knocks it out. Translational motion means the object is moving, it's changing position, as opposed to rotational. So that knocks it out. A pair of forces of equal magnitude acting in the same direction, that rules it out. They don't act in the same direction. A pair of forces of equal magnitude acting in the same direction, again, that rules it out, and our answer is A. So 12A. Of course, we saw that number 11, the best answer was D. And let's go to question number 13. Okay, number 13, we are given a uniform rod XY of weight 10 newtons. The rod is uniform. There is a reason that word is given. When you're given a uniform rod, its center of gravity is at its geometrical center. What that means, if the rod is 2 meters, then the center of gravity is 1 meter from either end. That only applies if the system is uniform. Okay. It has a weight of 10 newtons. Weight of an object always acts through its center of gravity, which is at its geometrical center, as we have already said. Now, is freely hinged to a wall at X. It is held horizontal by a force F acting from Y at an angle 30 degrees to the horizontal as shown. What is the value of F? What is the value of F? Now, this question is about moments. Moment. I want to start by saying that let's assume you're given a force here. This is its line of action, the dotted line. And you're given some point here. And then you're required to get the moment due to this force about this point. We would be required to get the distance from that point O, which makes 90 degrees with the line of action of the force, and then multiply that distance with this force. That is how we calculate the moment due to that force, or the turning effect of that force about the point O. So we are going to multiply F times D. Now, if that point is somewhere around here, you can see that the line of action passes through that point, and the moment of this force about point A is 0, because that distance happens to be 0. Very important. So we'll be required to always get the distance from the point about which we are taking moments all the way to the line of action of the force. And that distance must be perpendicular to the line of action of the force. Let's come here. And now you'll agree with me why this one is given here. Because the best method we can talk about here is to take moments about point X. What is the value of F? This system is in equilibrium. And let's assume this is the whole of this distance is D. Because this system technically looks like this. There's a force which acts that way. There's that distance there, which makes 90 degrees with the line of action of F. There's this other object here, and there is the weight, which is 10 newtons. I would want to take moments about this point, because that would be the best choice. So you can take moment about any point here. This point, this point, this point, or even this point. The choice of the point about which you take moments is determined by the forces which you want and which are known. For instance, you want force F. So you might want to avoid taking moments about point Y, because that will eliminate the moment due to F. It will make it 0. You don't want to take moment about this point, because it will make the moment due to this force, which you know, to be 0. So let's take a moment about point X, because we are not concerned with the forces which are acting at point X. In fact, the best way to eliminate forces which are unknown is to find that point through which they act, take moments about that point. You eliminate all those forces which you didn't know and you don't require them. If you take moments about another point, then those forces which you don't know will come into play. They will have moment about that new point and you'll be required to calculate them. The problem will work out fine eventually, but it will take you a long time. And this is one of the papers where we needed to save time. So you need to recognize that point about which you take moments first time. And one of the hints is look for what you have been asked to calculate. So you don't want to eliminate that. The next point is look for that point whereby if you take moments about that point, it will eliminate all the other unknown forces. And that happens to be point X. So let's look at the angles given. Over here I've got this angle which is 30 degrees. This other angle here is 60 degrees. Of course this is a 90. Let's call this distance here, let's call this D, because I want to express this in terms of D. In terms of D. How do we do that? If I call this distance here L, the whole of it, L, I'll be able to see that for me to get this distance here, I can use L because this one is a right angled triangle. This distance D is actually equal to L cos 60. This one. I just need to find the component of it. I resolve it in this direction. It will become L cos 60. I get D. And the distance from here to here is L over 2. So take moment. This one is important that you tell us you are taking moment about point X. The 10 Newton force tends to turn the system clockwise about point X. So you're going to have 10 times L divided by 2. Distance times the force. It's going to be equal to F tends to turn the system anti-clockwise about this point. And it's going to be equal to D, actually F, times D. But D happens to be L cos 60. Like that. And when you look at this expression, we observe that this L and this L will cancel out. This and this will give me 5. And F happens to be 5 divided by cos 60. Cos 60 from the calculator, it is 0.5. So I can do 5 divided by cos 60. I expect that one to give me 10 newtons. So the value of F is 10 newtons. And the answer becomes C. So that is how you would solve a question like that one. Remember here, it's not just a matter of knowing how that question is worked out. I'm assisting you to look at all the other important points as far as moments is concerned. In fact, when you are revising, don't just be concerned with the answer to a given question. That one you can easily check at the mark scheme and you'll be able to see it. That is not my aim. My aim is, number one, to show you how you arrive at that answer as far as that question is concerned. Number two is to help you review other important concepts that could be tested in the same question. And with that, let's go to question 14. And let's read the question together. We are told that 4 combinations of vectors are shown, each representing all the forces acting on an object. The forces all act in the same plane. The object is in equilibrium. So that means the resultant force on the system is 0. If I connect all those forces head to tail, they should form a closed loop. Or I can even connect them using some other methods, because I can see each one of these systems is connected differently. We are asked this question: which combination of vectors could represent the forces acting on the object when it is in equilibrium? Let's look at A. Now, let's start from here. First of all, the connection here is tail to tail. The connection here is head to head. All those two combinations or those two connections are wrong. The only connection that we have here, head to tail, this is the only one. So if we had gone ahead and reversed the direction of this one so that it now points in this direction, all the forces will be connected tail to head or head to tail, and the diagram will be correct. So over here, this is what rules this system out. Let's look at these connections here. Over here, I have these two, this one and this one, head to tail. But when it comes to the force which would make this system, for this force and this system, for this force and this force to be in equilibrium, is if I had a third force. The third force ought to be connected here and it ought to point like that. But again, that is not the case. So if, for instance, the two forces which are correctly connected is this one and this one, then the third one would be connected like this. Of course, in a straight line. Again, that, this, and this will be a head, tail to head. And that is the one which would be correct. But now, there is this force here which spoils everything. So again, that is why B is out. Let's look at this. Over here, this and this are connected correctly. So the third force, if this system was in equilibrium, would be connected like this. And it will be tail to head. And it will form a closed figure. Again, that is not the case. Let us now look at this. Over here, this force here, we can start here. We come like this. We come like this. Everything is okay. Then the third one would be connected here. Like that. But there is no problem because that force could be, we just need to slide it back like this so that its tail comes here and its head remains here. So it's only that it is being displaced differently. Just the same way as, you see this force here? It could as well as have been connected here. This one, it could be connected here. And it would still be correctly connected. Or the same force could still be connected here. See, this force. It can be connected in so many ways. It could even be connected here. You know, just push it back. So that is why D is the correct answer. That is the correct answer. So let me remove all the inking so that we can now say D is the correct answer. So remember, when you are given a force, a system of forces, and these forces and the system is in equilibrium, you need to realize that if you connect the forces head to tail, it's going to form a figure which is closed. Now, even if on the figure the forces don't appear as if they are head to tail, sometimes they can even appear to be tail to tail or head to head. For example, in this figure, which is correct, let me connect all these forces head to head and see what we get. This one here, I'm going to slide it back like this, so that this comes here. This one, I slide it back so that it comes here. And this one, I slide it like this so that it comes here. And you can see that figure is connected head to head. Again, it's going to represent a system which is in equilibrium, because this force tends to push, 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 and the resultant force becomes 0. I could connect it tail to tail. Let's see how that is possible. Let's look at tail to tail. All I need to do is, this one is tail to tail, no problem. I'm going to slide this one so that it comes here. And again, that is a system which is in equilibrium. Tail to tail, this, and this, all their tails connected together. Those are the concepts which you need to consider when you are looking at a system which is in equilibrium under the action of several forces. The forces could be 3, 4, it could be any number. But for examination purposes, they usually deal with 3 forces. So you need to be aware of what happens here. And that is how you would solve question 14. Now, in question 15, we are told that a rectangular metal bar exerts a pressure of 15,200 pascals on the horizontal surface on which it rests. The height of the metal bar is 80 centimeters. What is the density of the metal? This question requires us to consider the situation. It is a rectangular metal bar. It exerts pressure on the horizontal surface on which it rests. Okay, I'm going to say that is the rectangular metal bar. The pressure it exerts downwards is given 15,200 pascals or newtons per meters squared. The area, the height of the metal bar is 80 centimeters. So maybe let's say maybe it's, I can imagine it has a shape like this one here. This is what I'm imagining. Got a certain shape, and of course there is this area where the bar makes contact with the horizontal surface. This 80 centimeters, which is 0.8 meters, and then we are asked for the density of the metal bar. For us to do that, to calculate density, we need to know its mass and we need to know its volume. That means that the pressure it exerts on the ground will be force divided by area. The force it exerts on the ground is going to be equal to its own weight, which is mg, of course, divide by the area. Let's look at how we get mass from density. Mass is density times volume. So I'm going to say that the pressure, this one, is going to be equal to this mass will be density times volume times, of course, G, which is there, divided by area. Let's look at how we would calculate the volume of this metal bar. There is this cross-section area here, A. So the volume of this object will be the cross-section area times the height. Let me just shift my writing over here. So we are going to find that the density, we have the density, its volume will be the area times the height. Area times the height will give me the volume, this V, and then there is the G. The G is always there, and then divide by the area. And then we discover that this area and this area, they are going to cancel out. We need to get the density to be the subject. Density will be equal to pressure divided by the H times the gravitational field strength. The pressure is 15,200 divided by the height, which is 0.8, divided by G, which is 9.81. Let's see what that gives us. So first of all, I'm going to get 0.8. I multiply by 9.81. I get the answer. Then I'm going to get 15,200 divided by, I just click divide by the answer, and that gives me 1,936.7. 1,936.8 kilograms per meters cubed. Let's look at the closest one. 190 is very far. 1,900 is nearer that. So the correct answer for 15 is B. So our answer here is B. And let's go to question 16. In question 16, we are given that a mass attached to the lower end of a spring bounces up and down. At which points in the path of the mass do the gravitational potential energy of the mass, GPE, the elastic potential energy of the spring, EPE, and the kinetic energy of the mass, KE, have their highest values? We need to consider this situation. This is the situation. This is the mass. You know, there is that point where you can suspend the mass and then slowly release it until it achieves equilibrium and it does not oscillate. That is the situation we have here. So we are going to assume we are going to start from here. Now we can pull the mass down here. If we release it, it will come back to the equilibrium position, bypass that point, and rise through an equal height to that particular point. So if this is our reference point, I have that because I want to consider the gravitational potential energy. The gravitational potential energy will be highest at the topmost part because gravitational potential energy is mgh, gravitational potential energy. Kinetic energy is a half mv squared. This is kinetic energy. Elastic potential energy is given by a half kx squared. This is elastic potential energy. This is a spring constant, and this is the extension of the spring. So it has the highest kinetic energy when the spring has been stretched through a bigger value. This is x. That is x. So, bearing this in mind, we come here and we can see this is where it has the highest gravitational potential energy, GPE. The highest kinetic energy will occur where the speed of the mass is highest, and that is at equilibrium position. At equilibrium position. And the elastic potential energy is highest where the spring has been stretched through a bigger value. A bigger value. Stretched beyond this particular position. You see over here it was stretched, all right? If it moves back, the stretching or the extension becomes smaller. So if we continue stretching it, the elastic potential energy stored in it becomes larger. So it is at this point where it has the highest elastic potential energy. And let's look at the choices. Gravitational potential energy at the bottom of the bottom, no, at the top. Yes, that's true. Let's look at elastic potential energy. Elastic potential energy is at the bottom. Both of them are at the bottom. So this is the one which gives us the answer. Kinetic energy is highest at the middle. So the answer is C. So the correct answer here is C. Next, let's look at question 17. In question 17, what are we given? We are told a block of weight 80 newtons is pushed a distance of 60 centimeters up a slope inclined at 30 degrees to the horizontal. There is a friction force of 25 newtons between the block and the surface of the slope. And the information is illustrated here. What is the work G, the work WG done against the gravitational force, and the work WF done against the frictional force? So let's consider the situation. That's what we have. An inclined plane usually has a vertical height here, which can be worked out. Now the height that I'm concerned with is just this small height here. The small height here is what I'm concerned with, because the object is moving along the incline through a distance equals to 0.6 meters. From here to here is 0.6 meters. So the vertical height it gains is this one. And because I know this line is parallel to this, then this angle is also 30 degrees. Just like this one here is 30 degrees. So having said that, the gravitational potential energy GPE is going to be equal to mg times h. Mg is 80 and I need the h. How do I get the h? Let's look at this. If I do sine of 30, it will give me the opposite, which is h, divided by the hypotenuse, which is 0.6. So my h is 0.6 times sine 30. 0.6 sine 30. And that, we have to calculate it. give me 80 times 0.6 times sine 30, and I get 24 joules. So over here the answer is either A or B. So I've got to calculate the work done against frictional force, but it's better to calculate the work done by frictional force. And then when I bring in the work done against friction force, I can remove the negative sign. So it's going to be equal to the frictional force, which must be given here, friction force of 25 newtons, be given by the friction force of 25 newtons times the distance moved, which is 0.6. But you can see that the friction force is this way, and the distance moved is that way. So they are separated by a distance, an angle of 180 degrees. So I use cos 180 degrees. Cos 180 will bring in the idea of a negative sign. I'm going to explain in a moment why that is the case. So 25 times 0.6 times cos 180, I'm going to get negative 15 joules. Negative 15 joules. Now when we talk about work done by a force, we multiply that force by the distance that the force moves. The distance and the force must be in the same direction. If they are not in the same direction and the force makes an angle to the distance, for instance, if the distance is this way and the force is this way, and there is an angle here, theta, the work done by that force is always equal to F cos theta times D. In the case of frictional force, the friction force is right in the opposite direction like that, and the angle here is 180 degrees. We follow the same rule. We are going to say it is frictional force cos 180 times D. It is the cos 180 which is minus 1, and that is what makes the work done by friction to have a negative sign. Notice the word that I'm using. I'm using the word work done by friction. But the word used by the examiner there is work done against the friction. Let's see. WF, work done against frictional force. That word is here. Work done against friction force. When we say work done against the friction force, the word against takes care of the negative sign. So we won't include the negative sign. So we had already worked out the gravitational potential energy to be 24 joules. So the answer to this is B, where we have work done against friction being 15 joules. And let's go to question 18. So in question 18, we are given that a ball is dropped from rest and falls downwards and falls towards the ground. Air resistance is negligible, so we know that the acceleration is going to be uniform and the speed is going to increase uniformly. It will never reach terminal velocity. Which graph shows the variation with the speed of the height of the ball above the ground? So let's see. Which graph shows the variation with the speed of the height of the ball above the ground? As the height decreases, the speed is going to increase. Height above the ground is going to decrease. And since height above the ground is going to decrease, the speed will increase. So this is the situation that we have. There's the ground level. The ball is over here. And it's going to fall downwards like that. So definitely we know that the speed is going to increase with the time. But the height, which graph shows the variation of the speed of the speed, the variation with the speed of the height of the ball. In other words, one of the physical quantities we have is h here. And you can see that as the height decreases, the speed increases. They are inversely proportional to each other. So you can say that height is inversely proportional to the speed. As the speed decreases, as the height decreases, speed increases. They are inversely proportional with each other. And an inverse proportionality, when we are told that y is inversely proportional to x, this is what we do. We plot our y here, we have our x here, and that becomes the graph. It becomes the graph. Don't have any one of the quantities there, because when height is 0, the speed is going to be, when the height is 0, the speed is going to be very high. It's going to be very high. It's going to be somewhere here. In fact, it's going to touch here. When the height is 0, the speed is going to be very high. That makes sense. Makes sense. So a graph which is very close to that is C. It is C. It can not be a straight line like this because of the idea of inverse proportionality. What do we know about inverse proportionality? Okay, it cannot be like this because this one shows that when the height above the ground is 0, the speed is 0. That doesn't make sense. And here it shows that as the speed increases, the height is going to increase. That is not true unless that height was being measured from here. Downwards like that, but it's being measured from the ground. Height of the ball above the ground. So it must be measured from here. So that gives us the best choice to be C, but let's confirm that for number 18. So 18 is C, and indeed it's correct. So the correct choice for question 18 is C. And let's go to question 19. Now, question 19 is about efficiency of machines. We are given that power is transferred through a machine as shown. There is power input, which is Pi, into the machine. There is power loss, which is PL, and there is power output, which is PO. And we want to calculate the efficiency of that machine. Now, efficiency of a machine is usually the ratio of the output power to the input power expressed as a percentage. Sometimes you might just leave it just as a ratio, or leave it or express it as a percentage. Most of the time we would like to say the the efficiency of this machine is 80%, 90%. Instead of saying it that it is 0.9 to represent 90%, we express it as a percentage. But the fact remains that efficiency is the ratio of the output power to the input power. It can also be determined by the work output to the work input, because if you divide the work output by time, you're going to get power output. Similarly, if you divide the work input by time, you're going to get the power in. That is how we get that. But because the time is the same, the time for the output and the time for the input is the same, we can always find it as a ratio of the work output to the work input. This case, this is what I think about that. So it has nothing to do with the loss. We have already been given the power output and we know the power input. So it's the ratio between this and this. If we had been given the power input and the power loss, then you can say that the power output is actually the power input minus the power lost divided by the power input, because the power input minus the power loss is the one which gives us the power output. But I think there is no ratio like that one here. There's no ratio like that, because this one will just be a repetition of this one. So the best choice for that section is power output divided by the power input. And if you want, you can express it as a percentage. So the answer to that is D. Now let's look at question 20. In question 20, we are given that a tensile force is used to extend a sample of material. The force is then removed. The variation with the strain of the applied stress is shown on the graph. So we've got a stress, strain graph. Which point on the graph could represent the elastic limit for the material? Of course, the elastic limit I expect it to be point B. This is the elastic limit. It is the point beyond which Hooke's law no longer applies. The section where Hooke's law applies is the section where the stress is directly proportional to the strain. The stress is directly proportional to the strain, or the extension is directly proportional to the force. Let me review those two, because we know that stress is force over area, while strain is extension over the original length. Now, there is a physical quantity which we call Young modulus. Young modulus, which is the ratio of the stress to the strain, which is stress is force over area, strain is extension divided by the original length, and we get our equation as FL over AE, like that. So you can see that we still have an aspect of Hooke's law, because Hooke's law, which is represented by F is equals to KE, states that the extension is directly proportional to the force. The extension is directly proportional to the force. So you can see an aspect of Hooke's law over there. Actually, the same law can be expressed using Young modulus of the material. And when we plot the stress versus the strain, we are going to get the same point B representing the elastic limit of the material. So the correct answer for section 20 is B. Again, let me confirm. 20B. So the correct answer for 20 is B. And that brings us to the end of the second set of 10 questions. Remember, I did the first 10 questions yesterday. Today, I've done the next 20 in order to keep these videos very short. If you've not had a chance to look at the first 10 questions, the link is up there. So go through those 10 questions and please follow the kind of method that I'm using to teach you. When I teach you, when we look at a question, I don't just go straight to the answer. No, I show you the concepts which are related to that particular question. In other words, I look around that particular concept in order to remind you of those concepts. And that is what you should be doing for every topic or for every question which you use for revision. Always look around that particular concept so that you remind yourself of other important concepts. And as usual, if you're pleased with the way I handled this revision and you'd like some assistance, you can always get in contact with me and we can arrange how we can have some online lessons so that I can be able to assist you with the specific questions which you have in your revision. So until next time, when I tackle question 21 to 30, it is bye-bye.